Bismillahirrahmanirrahim. So today we will be having our 10th lecture and we will be talking about circuit analysis procedures. So there is a very thin line between circuit design and circuit analysis. So the advantage of circuit analysis is that we can have a very good and efficient design, and on the basis of that analysis we can reduce number of gates, or maybe we can have a lot more minimization. So that will be the focal point of our today's talk, right? So let's start, right? So these are the points which we will be touching upon one by one. Hazards, what are the hazards, and the glitches, right? And then analysis of digital circuits, right? And there are different methodologies, right? Where there are different steps that we have to follow while we are analyzing the digital circuits, right? And we can follow different approaches, right? We can use Boolean expression approach, and we can also have the truth table. So there are different approaches, right? And the advantage of this circuit analysis is that we ultimately have a minimized number of gates, right? Less number of gates mean minimized hardware, right? So let's start, right? So whenever we talk about gates, we normally apply input at the gate, and we have an output, right? So if I draw a gate, right? So we have an AND gate, right? Over here, and here we have two inputs, right? And this is the output, right? So normally how many combinations we have? Normally we have A, B, and this is the output. So we have 0, 0, right? 0, 1, right? 1, 0, and 1, 1, right? And then we have the output, right? 0, 0, and here we have 1. When both inputs will be high, we will get a high output, right? So the problem over here is the gate, it do not communicate the input immediately we apply the input at this gate, right? So there is some delay, right? If I apply 0, 0, right? So irrespective of the previous output, we will be getting a 0, but after a certain delay, right? So it means the output will not change immediately, right? So let's say that we are having this, right? Input 1, 0, and we are having 0 at the output. So and then after that we apply this input, right? So the output should be 1 immediately, but this will not happen, right? See, the problem is that the switching element within the gate, it react after a delay of finite time, right? So as a result, there is a delay between the propagation of input from input to the output. So this is the, if we say that we have 1, 1 over here, and this, as a result of this 1, 1, we will be having 1, and this has to be propagated at the output, but there is a delay, right? So then we have to give certain name to this delay, and we normally say this, right? This is the T, let me call it TP, propagation delay. If we are, for example, the output has to be from high to low, right? So I will call it high, low, right? if it has to be from low to high, so then I will call it propagation delay from low to high, right? And this is the high to low, right? So this is the delay which normally we have whenever we apply the input, right? And the output input, it shows its impact, right? Or it has to be changed regarding the input, right? So let's have a graphical interpretation, right? So here you can see that we have this is the ideal case. We have the input, right? And you can see that we have the transition, no switching time, right? You can see that as long as we receive the high, it will become high immediately with no delay, right? So this is the ideal case, or you can say that with zero switching time, right? But this in the real life, right, or in the real manufacturing point of view, this will not happen, right? We have to have a delay. So here you can see that we have a 0 because this is the level 0, right? And this is level 1, right? So you can see that there is a delay, right? And this delay is represented by TR, mean rising, because we are talking about the rising edge, right? So this is the time, you can say this is the time, right, which is TR delay, and we have this delay whenever we switch from 0 to 1, right? And for this amount of time, this remains 1 always, right? And then we have to switch from 1 to 0, right? So you can see that here, if you look here, you can see that there is no switching delay, right? There is no delay. It immediately, or it goes to 0, right? But here you can see that we have a fall time delay, which is represented by TF, right? And we normally say that this is the fall time delay, right? So this is if we talk about the inverter or complement, we have a X here, and we normally represent this with X bar, right? So here you can see that this is the input here, right? And this is the output. So ideally it should be, right? If I draw here, we can see that we have a 1 here, and if we start here, if this is level 1, right, and this is level 0, so this should be like this, right? Right? But this is not the case, right? So you can see that we have the input, but the output has not reacted immediately after we have the input, right? We can see there is a delay, PHL, right? Propagation delay, high to low. So it is high, and it has to be 0, so it lowers down after a certain amount of time. So this is the delay, right? So similarly, when here you can see that this becomes 0 over here, so it has to be high here, but there is no immediate response. So you can see that we have a greater time when we are having propagation from low to high, right? So this is the physical interpretation, or you can say the graphical interpretation of these sort of gate delays, right? And they are very natural. Then when we talk about the timing diagrams, we have to consider certain terms, right? like we talked about the gate delay, right? Time for the input has its effect, right, at the output, right? And then we can have minimum delay, right? If you look at here, you can see that somewhere we have minimum delay, right? And then we can also have maximum delay, so we can have those sort of terminologies, right? Then you have seen the rise time, right? Whenever we talk about this rising edge, right? So you can see that this is delay, and we represent this is the TR, rise time delay, right? And then fall time. So if we go back, you can see that this is the falling edge, and this is the TF, falling time delay, right? And then there is the pulse width. If I go back and I have to represent the pulse width, so I have to represent in this way, right? So this is the pulse width, right? The time it remains 1, right? So here you can see that this is the transition, right, from low to high, and here we also have the transition from high to low, and this is the actual pulse width during which the input remains high, or we have 1, right? So we can also have the pulse width, so you can have a sort of definition time that an output stays high or stays low between changes. If you talk about the low, so here you can have also the pulse width, right? This is the if you talk about, right, so you can say that this is the pulse width but with the low, right? So, and here you can see that we don't have any rise and fall time. We straight away have shown the high to low and low to high, but here we have the transition, right? So you can see that there is a transition time period, so you can say this is the transition time. So these are the terms regarding the timing diagrams, right? So we talked about the gate delays. So whenever we are making the circuit analysis, we cannot ignore the gate delays, right? You can see if we ignore, then we are only considering the steady state analysis. We are not taking into account the transients, right? Circuit transients. So this is very important that we should take into account the steady state analysis as well as the transient analysis, right? In order to have an effective and efficient design, we should always take into account the steady state analysis, right, in addition to the transient analysis, right? So let's talk about what are hazards and glitches, right? So a glitch is an unwanted pulse or signal at the output of a digital circuit, a combinational circuit, right? So you can say that a momentary change in an output that should not have changed, right? So this is a sort of unwanted signal. As we talk about, whenever we talk about the communication systems, we always have an unwanted signal, that is noise, right? Then whenever we transmit a signal from one place to another place, we normally have a noise, right? And noise is always an unwanted signal. So similarly, here regarding the circuit analysis procedure, a glitch is an unwanted signal, unwanted pulse at the output of a combinational circuit, right? So then we can have the hazards. A circuit that has the potential to produce a glitch, right? That it have the potential that there can be an unwanted pulse at its output, so that circuit is said to be having hazard, right? So then when we talk about the circuit analysis, right, then a circuit with hazards, it may or may not have a glitch, right? It all depends on the pattern of input, right, and the electrical characteristics of the circuitry we are considering. Like if we have a circuit, right, and for example we have different number of variables, like we have A, B, C. So we can have a different possible combinations, right? 0, 1, 0, 1, 0, right? 0. So when you talk about the hazard, right? So we said that a circuit with hazards may or may not have a glitch depending upon the combination of it input, right, and the electrical characteristics of the circuitry, right? So here if you apply a certain pattern of input, certain combination of input, your circuit may have a glitch, right? And moreover, your circuit can also have a glitch depending upon its electrical characteristics. For example, capacitance, inductance, and so on and so forth, right? So next we can say that a circuit having hazard may have or it cannot have the glitch, right? So we have to decide when do the circuit might have hazard, right? So let's draw a circuit over here, right? So we have, right, so we have, for example, a circuit over here, right, and then you have a AND, OR, and this is the XOR, right? So you can say that if we label them as A and this is B, right, and this is C. So we have 3 inputs, so there can be different possible combinations as I have mentioned over here, like you can have different combinations, and we have 8 different possible combinations of input pattern, right? We can have 1, 1, 1, or we can have 1, 0, 1, and so on and so forth. So we have 8 different possible combinations. But if we talk about the propagation of input from input to output, so there are different possibilities. Like you can see that we have different possible paths, right, from input to output. So here you can see that A is applied over here directly, right, and then we have A and B that are being passed through this AND gate. So there are different paths from input to output, so they are having different propagation delays, right? So that sort of circuit, it has the potential to have hazards, right? So now you might have understood that what sort of circuits they have the hazard, right? So those sort of hazards and glitches analysis, it helps us in circuit analysis, right? So there is a very thin line between circuit design and circuit analysis, right? So we analyze the circuit to determine its behavior, like we apply different combination of inputs, right, and then we talk about the electrical characteristics, right, and delays it can have. So then we analyze the circuit behavior, right, So if you have a two-level circuit, then analysis process is very simple. You can have a Boolean expression, right? But whenever you have multi-level circuits, the process becomes more complicated, right? So you cannot have the Boolean expression straight away. What you have to do, you have to write the Boolean expression for the intermediate stage, right? And then you move on. So we will try to focus on simple use cases for circuit analysis, right? So then regarding the circuit analysis, the circuit representation is very important, right? Like how you represent your circuit, right? So you can have a number of ways. By using them, you can represent the circuits, right? So we can have the truth table. If you have the truth table, you straight away can draw the circuit. You can also derive the Boolean expression from that truth table. But remember that the truth table representation is unique. You always have a unique representation for a certain circuit representation, right? And there is another way that is used for circuit representation, right? And that is you can also represent your circuitry, your design with the help of Boolean expression, right? But this is not unique. You can always have a number of expressions. So let me give you an example. For example, if we have A plus B, right? So what I can do, I can put a C plus C bar, right? So what we have, A plus B, C plus B, C bar, right? So this is equal to A plus B is equal to. So similarly, we also learned that A plus A bar, B is equal to A plus B, right? So they are equal, right? And we can prove that. Right? And that is equal to what? We will take A as common, right? 1 plus B, and then we have plus A bar B, right? So this is that is equal to A plus B. So this is also representation of A plus B, right? And this is also, if you talk about this, they are equal. So there are a lot of different representations. Similarly, if you talk about A plus B, and I can also represent them in this way, because this is always equal to 1, right? So this Boolean expression representation is not unique, right? And then we can have a circuit or gate representation, right? Or you can say schematic of the Boolean expression. So again, this is also not unique. You can have draw a circuit with 10 gates, right, performing a certain functionality, but you can draw the same circuitry with a less number of gates, right, performing the same functionality, right? So it means that gate representation is also not unique, but we always will be having truth table representation, right? Unique truth table representation, right? If you talk about A plus A bar B, right, whenever we will draw the truth table, right, we will be having, right, this same truth table 0 1 1 0 1 1, right, and we will be having, this is the output, we will be having the same unique truth table representation. Similarly, if you talk about the XOR functionality, and we always know that XOR, we have in XOR with two inputs, we have A bar B plus AB bar, right? So we will be having a unique truth table, right? We always know that 0 0 0 1 1 0 1 1, right? So we will be having this 0, right, 1 1, and here we have 0, right? So you can see that we have a unique representation if we talk about the truth table, right? So when we talk about logical circuits, right, we have two type of circuits: combinational circuits and sequential circuit, right? In combinational circuit, right, our output is, right, let me select the pen, right? So the output is a function of input variables, right? So this is the output. So we don't have to rely on the previous states, right? We don't need any sort of memory so that we can remember the previous states, right? So as long as we have the input, so we will be having the outputs. It means the output is equal to function of the input variables, right? So then we have the sequential circuits, right? But for sequential circuits, you need a memory, because you need to remember the previous state. You have to take into account the previous state, right? So you need a memory for that. So that is the main difference between those two type of circuits. We have a combinational circuits and we have the sequential circuit. But in this talk or in this lecture, we will be focusing on combinational circuits, where we have output, right, that is equal to the function of the input variable. So you don't need any memory for combinational circuits, right? Okay, and then for the combinational circuits, we can have different logics. Like here you can see we have AND OR logic, and we represented this as sum of products, right? You can see that here we have AND gate, right, product, and they are being summed up by this OR gate, right? So we have this logical expression or Boolean expression is right, and we can see that this is these are the products, right? We can say these are the products, and here we have the product again, and they are being summed up by this OR gate, right? And then if you talk about the input, we have 4 different inputs, right? So how many combinations we can have? If we have 4 inputs, we can have 2 raised to power 4, 16 different combinations that can be applied to this circuit. So you can see that we have different input. Like if you talk about this combination, you can see that we have, so these are the intermediate, right? So you can say that this is a sort of 2-level circuit where we have 2 levels, right? So these are the intermediate, right, stages, or you can say that we have if you look at the truth table, we have AB over here, right, and then we have CD over here, right? So you can see that we have the different results for that. So you AB, right, whenever we have both zeros, we will be having 1 at AB, because this is the normal AND operation. And if you consider the CD, we have CD 1 1 here, right, and 1 1 here. So you can see that we have a high over here, right, and this is the output, right? Either AB is high or CD is high, we will be having a 1. So you can see that here we have 1, right, AB is 1, and we have 0 at CD, and we have a 1 over here. So this is the truth table representation, you can see that we can have. So normally when we talk about the combinational circuits, we have different ingredients, right, that constitute the combinational circuits. Like we have in variables, different variables, right, and then ultimately we are using logic gates, right, and or not, and to represent those or to have the required functionality of those different Boolean expressions, right. And we have an output, definitely, so input, output, and the logic gates, right. And when we talk about the combinational circuit analysis, right, so there are different techniques, right. We can have the truth table analysis, right, and we can also use the Boolean expression, right, for their analysis, and then finally we can also have the simulations, right. But that third part we will not be discussing it right now, right. We will be focusing on truth table and Boolean expression analysis, right. So you can see that we have a truth table over here, right. Here we have the truth table representation, and we can analyze the circuit with the help of this truth table. Moreover, we also have the Boolean expression over here, and we have the circuitry over here. So you can also have the algebraic analysis, right. So as I've mentioned, that there is a very thin line when you talk about the circuit analysis and circuit design, right. So sometimes when you want to design a circuit, or when you want to draw a circuit, you normally can have your idea, right, in your mind, and you can straight away draw this on your paper, right. So here you can see that we have an example of an alarm circuit. So normally we have a panic, right, then we enable something, right, and people are exiting, right, and we normally look for secure exits, right. So you can see that, so these are the secure exits, right. You can see that window dot door dot garage, right, and you can see that we have a secure over here, right, and we will be replacing this. If you take those expressions as equations, so you can see that these are the two equations, and we have to replace this equation over here, right. So we have the alarm, panic plus enable, right, dot exiting, and then we have replaced the secure by window dot door dot garage. And if you talk about the circuit representation, then you can see that we have an OR operation over here between panic and enable. So this is, they are ORed, right. Enable with exiting bar, and then dot window dot door dot garage, right. So we have an OR operation over here, then we have AND operation. In some inputs are inverted, right. So you can see that we have window, door, garage, and it has to be inverted, right, due to this sign, right. So this is the design, combinational circuit design. And then we can have an example like this right here. So we have panic, right, then enable, then exit, right, window, door. The input are almost the same, right. So here we have some of the products, right. So you can see that we have AND gate over here that represent the product, and we are multiplying or performing the AND operation between enable, right, then exit, and it's in complement, and then window also complemented, right. Ultimately those different AND operations, if I name it A1, A2, right, and then A3, they are being summed up by this OR gate, and you can have this panic plus enable dot exit bar window bar plus enable dot exit bar door bar, right, plus enable dot exit garage, and they are complemented, right. So this is the alarm circuit transformation, right. So let's have a problem, right. So how we can convert from a circuit drawing to an equation or a truth table. As we talk about that, we have if we go back, right, so here you can see that we have different circles, right, and then you can see the arrows, right. So you can say that they can, so if you have a truth table, you can have the Boolean expression, and if you have the Boolean expression, you can design or represent it with the help of gates, right. So that's what we have to talk about the problem, right. We have to draw a circuit from an equation, right, or from a truth table, or you can also say that we have to convert from a circuit drawing. So we have a circuit over here, and we have to find out the equation, or you can say Boolean expression, or you have to draw the truth table, right. So there are different way outs. Here we have two approaches, right. What we can do, we can have intermediate equations, or we can have intermediate truth tables, right. If you talk about this circuit, right, you can see that we have the intermediate steps over here, right. So first of all, what we have to do, we have to label all the gate output. If you talk about this AND gate, it has 3 inputs and we have an output, right. So we label it as R, right. And if you look at this OR gate, it has 2 inputs, and we have represented the output of this OR gate as with an S, right. And here we have an AND gate that is being fetched by this S and C bar. So we have a T as an output of this AND gate, right, and finally we have the output, right. So we have to label all gate outputs that are function of it. So here we can see that this R is a function of if A, right, B, right, and C, right. So this R is the function of right, A, B, and C, right. So similarly, this S is the function of A and B, right. Then we have to label gates that are function of input variables and previously labeled gates, right. So on the second step, we have to label gates that are function of input variables, right. And then we have to repeat the process unless we reach the output. So you can see that this output, right, if you talk about this T, right, so this T is the function of, right, S, right, because we have a S over here, and C bar, right, and this output is a function of, right, R, and here we have T, right. So this is the, so we will keep on going unless we reach the outputs, right. So let's have the approach 1, right. So first we have labeled, right. So now we are using a specific approach. We are creating the intermediate equations, right. So we are actually calculating the intermediate Boolean expression. So here we have R, and you can see that we have the AND operation over here, so R is equal to ABC, right? And here we have an OR gate, right? So this OR gate, right, we have S as an output, so S is equal to A plus B, ORed with B, right? And then we have a T over here, so this is equal to C bar and S, because this is S, right? And finally we will have the out is equal to R plus T. So we will be going in a sequence, right? So we start from here and then we calculate R, then we computed S, right? We represented S, right? And then we computed T, and then finally we reach the output. And then we have to form the relationship based on the input variables A, B, C. So what we have to do, you can see here we have R. We have to represent R in terms of A, B, C. Here we have S. We have to represent because but they are already in the form of ABC because we have input ABC and this is the output. So over here we have to make some sort of substitution, right? So you can see that we have T, C bar, S, and this S will be replaced by A plus B, right? And then finally we have the output, then that is equal to R plus T, right? So we have R in terms of ABC here, right? And then we have a T in terms of ABC here. So that's the representation, right? Or representation in terms of ABC, because we have to relate the output to the input, right? So if you talk about the input and output, so now we can say that the output is a function of A, B, and C, right? So you can see that here, over here we have only ABCs, right? So here we have ABC, it is AND operation, then we have the OR operation over here, OR operation between A and B over here, and then this is ended with C complement, right? So this is the second step, right? And then we have the third step, right? Then we have to expand the equation in a sum of the products way out. So if you look back, so here we can multiply this C, right? This C bar with A and B. So this is the same here, right? You have multiplied this C bar with A and A ORed with B, right? So we have ABC, AC bar plus BC bar, right? So this is the expanded sum of the products final result, right? And then now we will be having the second approach, because in the first approach, what we did over here, we have we find out the intermediary Boolean expressions, right? And then we labeled labeled all those expressions, right? So that we can have their expression as the input variables, right? So here we have another methodology, another approach, and that is truth table, by using truth table. And this truth table representation is unique. We will always be having a single and unique truth table for a given circuitry. So here you can see that we have 3 different variables ABC, and we have 8 different combinations. If we start from 0, right, 1, 2, 3, 4, 5, 6, right, and then 7, right? So we have all possible combinations of A, B, C, and we have to compute R and S because they are the next variables which we come across. So if you talk about the R, so you can see that this is the AND operation between ABC. So we'll be having only 1 over here, because we normally, or the truth table tells us that when all the inputs are high, we will get the high, right? And then we have to compute S, right? So here in S we can see that we have 2 inputs, A and B, and the operation is OR, so we have to focus on A and B. So whenever A is high or B is high, we will be having a high. So here we have A0, B1, A0, B1, so we will be having a high, and this is high, right? So whenever we have one of the input high, or we have both input high, we will be having 1. So you can see that we have the S over here, right? So next we come across T, right? So now we have to, you can see from the diagram that T is the output of this AND gate, and the inputs are S and C bar. So we have to take the complement of this C, right? So you can see 0 1 1 0, 0 1 1 0, right? 0 1, and so on and so forth. So this is the complement of C, right? And then we have the S, so this is the S, and we have to compute the AND of this C bar and S, right? So we have T, right? So you can see that 1 0 0. So where we have both ones, so here we have both C bar and S1, so 1. Here also 1, right? And here also 1, so we will be having T. So next, you can see that T and R, they are summed up by using the AND gate, right? So there is an OR operation between R and T, right? So whenever we have one of the R or T high, or both are high, we will be having a 1. So you can see that here we have T high, so we have a high output, right? So high, T is high, so high output, right? So here we have both inputs are high, so we have a 1, right? So this is the way out, right? So, and you can have, so this is the truth table solution, right, for the analysis, right? And then if we have more than 1 levels, or we can have more than 1 output, then how we will be handling the circuit analysis. So this is a more complicated example. So you can see that we have 2 outputs, right, F1 and F2, right, and we have 3 inputs, right? So you can say that multi-input, multi-output. So we have multiple inputs and we have the multiple outputs. So how we will be handling, so if we talk about the Boolean expression, you can see that we have the intermediate labels, right? So this is T2, T1, right? Here we have F2 bar, right? And this is the T3, and this is F1, F2. So you can see that we have intermediary expressions, right? So you can see that we have a T2 over here, and T2 is equal to A, B, C, right? And we have a T1 over here, and that T1 is an OR operation between A, B, C, right? And then we have F2, right? And that F2 is equal to that F2, right? Here F2, we have a F2, this is the F2 bar, right? So we have AB, right? AC and BC, and they are ORed by this OR gate, right? So, and then we have to calculate T3, right? So you can see that we have this level sort of, and then we move to the next level. So this is the first level, 1, 2, and then we have 3 right, different variables or expressions at this level, and then this is the second level. So we have only T3 at this level, right? And so you can see that T3 is equal to F2 bar T1, and F1 is equal to, this is the final, or this is the output, so F1 is equal to T3 plus T2. If you take all those Boolean expressions as equations, then you have to substitute different equations in order to find the solution. So our ultimate goal is to represent F1 and F2 as in terms of A, B, C, right? So here you can see, if we talk about the F1, we have F1 is equal to T3 plus T2, right? So T3 is equal to, you can have a look over here, F2 bar T1 and T3, T2 is equal to ABC, right? ABC are ended, right? All the 3 variables are ended, right? And then we have F2, right? Here AB, AC, right? And but we have a complement over here, and then we have A plus B plus C, right? So this is what? This is T1, and finally this is the same expression. So here you can see that break the line, change the sign, break the line, change the sign. We have used the De Morgan's law over here. So you can see A bar plus B bar, right? A bar, right, plus C bar. So break the line, change the sign, and then when we are solving the individual, because if we break this line and change this sign, we will be having a dot here, a dot here, and these are the complements, right? So here we have used another Boolean law, right? So let me write down the Boolean law. So we have right, if I want to represent this A bar B bar, right? So what I will be doing, right? So I can write here A bar plus B bar C bar, and that is equal to A bar plus B bar. So this is, as I know that A plus A bar B, that is equal to A plus B, right? So I can represent, and those values, they are being multiplied. You can see that A bar is multiplied with B, right? A bar B bar, A bar C bar, then C bar B bar, and then we have C bar C bar, right? So you can always have the simplification after the after using the Boolean laws, right? So our ultimate goal is to represent F1 in terms of input variables. So we have F1 here in terms of A, B, C, right? So here we have another example, but another way of solving the same complicated example. So we have used the truth table approach over here, right? So you can see that we have 3 input variables, then we have represented the intermediary stages of that circuit, F2, F2 bar, T1, T2, T3, F1, right? So you can see that we have so here if you talk about the T2, so T2 is an AND operation, so we will be having only 1 over here. And then if you talk about the T1, so T1 is an OR operation between, so whenever we have a 1 at any one of the ABC, or we have all 1s at ABCs, we will be having a 1 at T1. So similarly you can compute F2, right? So here F2, right? And then we have F2 bar, right, which is here we have to just complement the F2, we will get the F2 bar. So this is the, so here we have ABC, as I have labeled them properly, so we will be having this, right? So this is the final expressions for both the outputs F1 and F2. So this is the one possibility, right? And then we can also use the truth table approach, right? So you can have 8 different combinations. We have 0, 0, 0, we have F1 0, F2 0, then we have, so we can have this output, and then we will be having all the inputs, and we can compute the output. But it's a bit difficult if you straight away use the truth table in this way, you can make a mistake. So that's why it's more better for us that we can have some intermediate stage, like I have shown in one of the previous slides, right? So here we have another combination of inputs, right? And I have the output, right? And finally we have the truth table for all the possible input, and so multi-input, multi-output, right? So 1, 1, 1, and we will be having this. And you can also use the K-map, Karnaugh map, in order to have the simplified expression. So you can straight away draw or map this F1, right, over here, right? So you can see that, and you can also have the simplification and K-map mapping for the second output, which is F2, right? So that's all for today's lecture, right? So today we have studied the circuit analysis, right? And we talked about the combinational circuits, sequential circuits, and we focused on the combinational circuits regarding the circuit analysis, right? And we used 2 approaches. One is we analyze the circuit by using Boolean expressions, and then we tried another approach, that is the truth table approach, right? So that's all from my side. So अपना बहुत ख्याल रखिएगा और मेरी तरफ से अल्लाह हाफ़िज़, अस्सलाम वालेकुम।